Just recording here. I'm not on mute. That is a good thing. Okay. So, some development. Hopefully you're not upset about it. But what we decided, everyone teaching Math 120 decided that we will not do a final exam this year. So we will not have a final exam. And hopefully that's good news. So I marked test number 2 finally. Nice work. I know, right, Chloe? Hopefully everyone's kind of, well, at least the 3 of us still. Hopefully it's a good thing. Hopefully good news. Hey, I keep wanting to do a question mark. Awesome. Good. So I thought it would be good news, but you never know. So what people might get upset about. Test 2 was really, really good. So I'm just so glad that we got that done, and your marks are on Moodle. Yeah. I will email marked tests back to you. Later today. Oh, oops, I should say later. So I will email the marked test back to you, but once I mark them, I had to move on to some other more pressing things, but you will get them back. And so the new grade breakdown, can't write at all today. New grade scheme is going to be 25% assignments and 75% tests. And more hopefully good news is that we're actually going to finish the material today. And because we don't have a final exam, I really don't see the point of doing a final exam review. So, I mean, we could potentially be done after today. And seeing as there are only 2 people here, maybe that's a good way to go. So, so we will finish the material today. We will finish the material today, right? 7.3, 7.4, and 7.5. Sounds like a lot, but it's not really. So we will finish the material today. And since we will not have a final, so since we will not have a final, there is no need for final exam review classes. Which means this will be our last class. Sad face. Sad for me, but I'd be sadder if we were meeting in person. Now that it's just me talking to a screen, basically. It's not as sad. So I guess it's easier. So if you have any questions about just kind of how this course is going to wrap up, we'll finish the material today, and then, but just let me know, right? Especially if the 25% assignments is a concern for you, then let me know. The tests, I told you there was some point to us wrapping up with a test, and so it kind of panned out. So I'm glad, because you guys worked hard, and now I think you deserve a little break. And I'm sure you've got other things going on anyways, so yeah. All right, I'll check to see if there are any questions. Any questions, comments, concerns? I see none. Great. All right, so what we'll keep going through is chapter 7. So what we were finding last day was chapter 7 is a little bit tricky, just because oh, when are all the assignments due, asks Chloe. You know what, I think I put let me see here. Let me see if I can go to WebAssign. Looks like 3, 4, 5. Let's see. Oh, probably didn't want all of those, but whatever. These are all the homework problems. Okay, I don't have a pointer, but looks like chapters 3 through 6 are due April 3rd, and then chapter 7 is due April 12th. Okay, so here, I'll just put that here. Chapters 3 to 6, I'll call them assignments. Assignments are due April 3rd at 11:59 p.m. And then chapter 7 assignments are due, I want to say April 12th. I'll just double check though, April 12th at 11:59. Let me just double check though. Yeah, looks like April 12th to me. Awesome. Make sure. Awesome. Cool. All right. So, all right. So let's get cracking on the rest of chapter 7 here. Home stretch came faster than we thought it would, or at least than I thought it would. But we had this email exchange going back and forth over the weekend, and then we just kind of landed on no final exam for you guys, because I'm happy with what we've tested and all that fun stuff. So that's what we landed on yesterday. So good news all around. So 7.3, I can't even remember what it's called, but 7.3, oh, the double angle, half angle, and product sum formulas. Double angle, oops. Half angle, oops. Half angle, and product some formulas. And one thing to keep in mind about most of chapter 7 is it's just introducing different things that we could use. So chapter 7 is not really about memorizing, right? A lot of these things you would have available. So all the formulas that we're going to talk about, you of course would have available to you. They're not worth memorizing. They're really long and there's a lot of them. So there is no need to memorize, to memorize any of these formulas. You know what, I'll put this on its own page just in case I think of something new, and also it's nice to start a section on a fresh page. There's no need to memorize any of these formulas. Okay. We need to know that they're available in case we need them. So we need to know that they are available in case we ever need them. Yeah. So it's going to feel like a lot, but if I just go and I pull in some of these formulas, right, we can start with the double angle formulas. Notice that it's a double angle because we've got 2x and 2x, right? So here, double angle, right, that's why they're double angle formulas. We need these in case we've got these double angles and we don't want the double angle. Then we've got options for, and especially for double angle of cosine, we've got a lot of different options here. And so we can rewrite them in terms of just sine and cosine, right? Which was one of our tricks for our proofs, right? It was rewriting everything in terms of just simply sine and cosine. So if you've got this double angle that you don't want to deal with, here's another way you could write it. Same thing for cosine and same thing for tangent, right? We go back here. We can even do things like, we can use the double angle formula to deal with higher angle formulas. So we can use double angle formulas to deal with, I'll call them higher angle formulas, right? And so that's what this example is all about that's in your handout, right? So what we did was, okay, well, I've got the cosine of 3x. Sorry, I don't know if you can hear it, but they're vacuuming the hallway, and it's so bizarre. I feel like they never vacuum the hallway, but then it has to be right now, so it's really distracting, but that's okay. So we can rewrite the cosine of 3x, right? So that's the triple angle. We can rewrite 3x as 2x plus x. And then we've got a double angle, but also we've got an addition, right? And so we can use those addition formulas from last day. And yeah, it's like they never, it's so weird. Okay, anyways. So we can use the double angle formula here, but we've also got this addition. So once we break it up, right, we've got an addition, a double angle inside the addition, and then just the x. And so we can land at something like this after we kind of work through it. This one you've got, so let's not do that one together, but just wanted to show you that that can be done. So there's also things like if you want to lower the powers, right? So here we've got sine squared, cos squared, tan squared, right? Usually it makes it right. Oh, I shouldn't cover the square, I guess. Right, so here we're going from powers of 2 to typically some sort of double angle, right? Depending on the situation, to double angle. Oops, double angle, oops, angly. Angle formulas. Okay. Kind of situation dependent. Sometimes we might want to go from this double angle setup to something more concise like sine squared, right? So it goes both ways, right? It would mean you'd have to recognize something like this and say, oh, well, obviously I can replace it with tan squared. I don't see anyone being that well versed in trig identities to be able to see that right away, but I don't know, just knowing that they're available helps. Let's see what else we've got here. Okay, so we'll do an example here. We won't do a ton of examples for these because just like last day, right, a lot of it is just going to be you practicing, and now with no final, I don't know if there's a point, but why would I say that? So here, what I've got, let's do one like, let's do 14 maybe. 14, because once we see the trick for dealing with cos to the power of 4, we can do the same, we can apply the same trick again to do cos to the power of 6, right? So this one's just a little bit more interesting because it's got the 4 and the 2. So if we've got cos to the power of 4 of x times sine squared x, we know that this is just cos squared x squared, right? Because we said, and then same idea, if we wanted to, times the sine of x squared, right? Because the squared can move inside here if we wanted it to, right? Or out if we need it to. So depending on the situation here, I might actually keep the square on the sine, right? Because if I want to use the formulas for lowering powers to rewrite the expression in terms of the first power of cosine, so I want to rewrite this thing in terms of just cosine. So I've got a sine in here. This one's in terms of cosine. So notice that all of these formulas for lowering powers, they only involve the double angle of cosine, which makes sense because here, the double angle of cosine has a lot of different options, right? And so it's a lot more versatile, and that's probably why we were able to write all these in terms of cosine. And so what we want to do is we want to rewrite in terms of the first power of cosine, which is just cos of x. So what I'm going to do is I'm actually going to not pull that square out because that's going to make it easier to rewrite in terms of cosine, because then I've got this sine squared x here that I can rewrite as 1 minus cos 2x over 2. So how I'm going to write this is I've got cosine squared x squared. I'm going to separate that. The reason for that is because here I've got cosine squared, which I can rewrite in terms of the first power of cosine, right? It's just going to happen to be squared here, all on the outside. And then I've got the sine squared. So times the sine squared of x. Now I can apply these the formulas for lowering the powers. So I get 1, and I'm going to put big square brackets around here, 1 plus the cosine of 2x over, running out of room here, over 2 all squared times, and maybe I should make it clear that that's the cosine of 2x, just so it doesn't look like a cosine squared. So then sine squared x is 1 minus cos of 2x over 2. Okay. So what I've got here is so if I bring in the square, right, then it goes on the numerator and the denominator. So what I've got here is I've got 1 plus cos of 2x squared over 2 squared all times, and then I'm just going to leave the 1 minus cos 2x over 2. So what I'm going to do is I have to bring in, I have to expand this square, right? Being very careful that you don't just bring in, right? We can't expand that 2 out. In fact, I'm going to give myself a bit more room here so I can show that 1 plus cos 2x times 1 plus cos 2x. That's going to be the safest way to expand this thing, over 4, times 1 minus cos 2x over 2. Okay. So what I get is I get 1 times 1 is 1, 1 times, so plus cos 2x plus cos 2x plus cos 2x squared, cos 2x squared all over 4. Got tricky. Times 1 minus cos 2x over 2. So let's see here. Hopefully this works out. 1 plus 2 cos 2x plus cos 2x squared over 4 times 1 minus cos 2x over 2. I'm multiplying, so I've got a fraction here and a fraction here, but I'm multiplying, so I'm allowed to multiply across here. And what I'm really hoping is that this square is going to go away somehow. So here we go. I get 1 times 1 is 1 minus cos 2x plus 2 cos 2x minus 2 cos, oops, not x, 2 cos 2x squared plus cos 2x all squared minus cos 2x to the power of 3. Dun, dun, dun. I don't know, I'm gonna get myself out of this mess. Over 6. Oh, sorry, 4 times 2 is not 6. 8. Okay. Well. I can cancel some stuff, but is it enough? I might have put myself down a rabbit hole here. 1 minus 1 cos 2x plus 2 cos 2x puts me at plus cos 2x minus 2 cos 2x squared plus cos 2x squared. So that puts me at minus cos 2x squared. Cos 2x squared minus cos 2x to the power of 3 over 8. I don't know if this counts. In terms of the first power of cosine. Cos to the power of 4 sine squared. Well. What other tools can we use? Nothing quite yet. I see one thing that I can use. If I have a 2 cos squared x minus 1, but that brings me back to a cosine squared. I wonder if we need to deal with this. Do we need to deal with this? With these, I guess I should say. Or are we done? Good question. I know you're saying that. You tell me. Hey, cos 2x minus cos 2x squared. How about we're done? I don't know. I don't know. Let's do something more fun. Well, not more fun maybe, but I would probably look those up, but I'm also not that concerned about it. But because that was confusing, check if there are any questions. See none. All right. So the half angle formulas are when the angles are just some angle u over 2. And then the plus minus just depends on which quadrant the u over 2 lies in, right? And so remember, if you're taking the first quadrant, quadrant 1, 2, 3, and 4, then it's what is it? All students take calculus, right? So here, all are positive. Sine is positive. tan is positive, and here cos is positive. Maybe I'll highlight this. All students take calculus. Or I know some high school teachers do cast, but I find it very confusing to start in the fourth quadrant, so all students take calculus makes more sense. Or I've also heard all suckers take calculus, but I prefer all students take calculus. So here again, these are not things that you need to memorize at all, right? It's just being able to use these things and being able to recognize that, oh, I'm taking a half angle, right? So the sine of u over 2, or even if it's easier, you can rewrite your angle as some half angle. So then this is a half angle identity. There's also things, so this is just kind of going back and forth. So I'll bring them both in at the same time. But the product sum formulas, right? Here we're moving from a product to some sum. Or I guess it even says product sum. And then so here's a sum. Whereas here, if you're moving from a sum, you can rewrite it in terms of a product. Right, so it just depends on the type of usually proof that you're working on, right? Whichever way is easier. And there's a lot of proofs that we could do here. Remember, proofs are nice once you kind of get the hang of it. But there's not much I can teach you about proofs besides saying, okay, well, you start with the side that's the trickier side. In this case, I'm not sure which one it would be, right? I would probably start on the left-hand side and then work my way over to make sure that I get to the right-hand side. So what I've got here is, let's do number 80 together. Just something. And like I said, you don't have to do any proofs on the final exam anymore because there is none. So I'm not too concerned. So the tangent of x over 2 plus the cosecant of x show that it equals, or usually I have a question mark, but equals 2 minus cosine of x over the sine of x. Okay. So what I'm going to do is I'm going to start on this side. So start here, rewrite until it looks like the right-hand side. So I'm going to start with tan of x over 2 plus cosecant of x. And here, this is a half angle. So I'm going to start there because I recognize it right away. So I'm going to use the half angle of the tan of x over 2, or u over 2. And in fact, I'm just going to, because it's nice and long, I'm just going to bring it over here. Oops. Paste image. So I've got the tan of x over 2 is, I can rewrite as 1 minus the cosine of u, which is just x in this case, cosine of x over the sine of x. And I can't tell if it's a, I think it's an equal sign. Weird. Why can't we see? Am I going to be able to find it? Which section is this? 7.1, 7.2. Half angle. So it is equal to, you know what, I'm just going to steal this one because it's a little bit nicer looking. Yeah, that's weird. I think because Jenna had to take screenshots. Okay. So looks like we've actually got two options here for the half angle for tangent. And so what we've got is we picked the first one just because I thought it was going to be minus here, but it's not. It's equal to. So here, I'm just going to point you down here. But let's stick with the cosine and see what happens. I can always switch it back, or if I find that it's not going to work, then plus the cosecant of x. I'm actually going to look at the formula sheet to see if there's any anything that I can use for the cosecant. I've got the cosecant squared. Are there any other spots where I could replace that cosecant with something a little bit nicer? I could move the cosecant into something in terms of cotangent, which might be nice here. And then I've got the tangent. What else can I do? Oh, tan of 2x. Half angles don't seem to be on here even. So tells me probably won't use them. Let's use the basic identities then. Cosecant of x is 1 over sine x, which I'll replace right away. What's nice about that is it gives me a common denominator, which puts me at 1 minus cos x plus 1 over sine x. Now, what was this? Hey, we're so close. We just wanted to show that it was equal to 2 minus cos x over sine x, which we can, because 1 plus 1 is 2, and then minus cos x over sine x. So that's probably enough proofs. I know there's some harder ones, right, kind of down at the bottom here. Might be worth a shot just for fun, right? You'll know if you've reached the end, and it's pretty satisfying, but let's not worry about it. So 7.3, that's it. Okay, so a lot of formulas, right? Nothing that you need to memorize at all, even for future courses, right? If you're ever going to need these, remembering that they exist, that's the point. And then the 7.4 and 7.5, lecture notes have been combined. They're all just squeezed onto one page. So here we go. So sections 7.4 and 7.5, trigonometric equations. I think it was trig equations. Yeah. So what we have is, remember on the test we said, okay, we'll solve for one of the solutions, right? And so for this section, if we're solving things of the form sine theta equals A or cos theta equals B, something like that, then we find all the solutions in one period, right? And so by default, sine and cosine have a period from 0 to 2 pi, right? So between 0 and 2 pi, so essentially one revolution around a circle, right? And so here, find all the solutions essentially on the unit circle. Zero to 2 pi. Then what we do, so there could be spots, there could be multiple spots where the solution is on this unit circle. So there could be more than one solution in one period. But then to find all the solutions, find all solutions by adding multiples of 2 pi to each solution from step 1. So if t is a solution found in step 1, then t plus 2 pi k would be a solution for any integer k. Okay. So it goes back to finding one solution or all the solutions in one revolution. But then once we have those, we add 2 pi k, right, making room for, so for example, if this here is a solution, right, let's say there's only one solution, then plus 2 pi plus another 2 pi, oops, right, and so on and so forth, they all end up at the same place. So as long as we're adding 2 pi, we'll go around the circle once. So there is an example walking you through it. Let's do, let's start with just the little one. Okay. So remembering that on this circle, right, we've got x and y values, right, but x is the cosine of theta and y is the sine of theta, right? And so if we go and we grab our unit circle that you want to have handy, where did I put those formulas? Trig formula sheet, there. The unit circle might be the easiest one to use, right? We could use the table if you want to. That works too. But I like the whole unit circle because then we can make sure that we've hit all our options. So if I put this over here, so we want to find if we have to solve the given equation. So if we start with, I don't know, let's start with 8. Cos theta equals root 3 over 2. Well, root 3 over 2 has to be our x value, right? Because we want cos theta. And so root 3 over 2 must be the x. So if we go through and we highlight root 3 over 2 happens here as our x. That's negative root 3 over 2. That's going to be different. And root 3 over 2 happens here. Maybe I'll clean that up a little bit. Root 3 over 2, root 3 over 2. So we have one solution, two solutions. Okay. So between 0 and 2 pi, we have two solutions. Oops. We have two solutions. We have theta equals pi over 6 and theta equals 11 pi over 6. Okay. So what we can do is, I think the easiest way to do it is, so therefore all solutions are when we have theta equal to pi over 6 plus 2 pi k, for k equal to 0, 1, 2, all the way up to infinity technically, and for theta equals 11 pi over 6. Oops. Pi over 6 plus 2 pi k again, for k equal to 0, 1, 2. We could spend some time and combine these, right? This is still true, right? When we talk about these solutions broken up, it would be easier if they were just kind of opposite each other, right? Then I would go a distance of pi, and then another pi, and then a pi, and then another pi, 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 pi. But here I'm going from this pi over 6, I'm moving 2 pi, and then I'm moving 2 pi, and then I'm moving 2 pi. And then from 11 pi over 6, I'm moving up 2 pi, 2 pi, 2 pi. So I could figure out what the interval is in between here. I'm not too worried about it though, because I don't know, this is a legitimate solution. So we could make it fancier and combine it, but we don't need to. So I will put that in here. We could combine this into a single solution. I say single in quotes because it's all the solutions. So there's infinite solutions, so it's not really a single solution. But we don't need to. So let's see here. We go back to our notes. We could do the same thing for something a little bit more complicated, like these guys. Okay. Let's see here. So find all solutions of the given equation. Let's do 34. 4 sine squared theta minus 3 equals 0. Well, I only know the solutions in terms of sine theta, but what I can do is I can just move things over to the right-hand side and see if I end up at a solution that I'm used to. So I can have 4 sine squared theta equals 3. So sine squared theta is 3 over 4. I can take the square root of both sides, so I get sine theta is the square root, and it's the plus minus square root of 3 over 4, because when we take the square root, we get the plus and the minus. Root 3 over 4, which doesn't really match anything on my unit circle, but I see right away that I could rewrite it as root 3 over 2, because this is going to be, so sine theta is the plus minus of root 3 over root 4, which is the plus minus of root 3 over 2. So sine theta is root 3 over 2. Let me just see if I can copy this thing. Copy. Paste. And I'll just erase this from the previous question. And let's see here. So sine is the y value, right? And so I'm looking for plus or minus root 3 over 2. So here I am, not so sloppy maybe. Positive root 3 over 2, positive root 3 over 2, negative root 3 over 2, negative root 3 over 2, and those are my solutions. So I'm at pi over 3, I'm at 2 pi over 3, I'm at 4 pi over 3, and then I'm at 5 pi over 3. Right? So these are my solutions in 0 to 2 pi. If I list them, is going to be that theta is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, so if I go from, looks like if I go from pi over 3 to 4 pi over 3, and it makes sense, right? Then I've gone a distance of pi. But then I've also gone from 2 pi over 3 to 5 pi over 3. I've also gone a distance of pi, right? And so here, what I can say is from pi over 3 to 4 pi over 3, I've gone a distance of pi. And then from 2 pi over 3 to 5 pi over 3, I've also gone a distance of pi. So it looks like as long as I start at one of these starting points, right, pi over 3, then as I can just move a distance of pi each time, and I can capture all those solutions, right? And same thing, if I start at 2 pi over 3 and I move a distance of pi instead of 2 pi, then I'll be able to catch all of those solutions every time. So our solutions are that theta equals pi over 3 plus pi k, right? Because now, no longer 2 pi, right? Because it's a distance of just pi. Confusing. For k equal to 0, 1, 2, and also theta equals 2 pi over 3 plus pi k for k equal to 0, 1, 2. Again, we could combine these and find some sort of overlap, right? But because we're moving, well, we would use the fact that we're moving the same distance between here and here, and then there, and then here, and then here, and then there. But I wouldn't bother. This is a fine solution. right? Breaking it up into two parts, it's just easier to look at. Okay. So let's see what else we've got here. So it says sometimes we can solve trig equations by factoring and using other equation solving techniques that we've learned this semester, right? And so we can use things like factoring, collecting like terms, quadratic equations even, right? To solve equations. So if we want to solve equations by factoring, for example, right? I'll have a bite of 43. We'll see how it goes. 3 sine squared theta minus 7 sine theta plus 2. What I'm going to do is I'm just going to temporarily replace sine theta with x, right? So what I get is I have 3x squared minus 7x plus 2. If I have to solve these equations, right, for sine in this case, right, or eventually theta, I know how to solve for x here, so that's going to be a good start. So I can use quadratic formula. Right here, a is 3, b is -7, and c is 2. I feel like if this course taught you anything, it's the importance of the quadratic formula, right, or the quadratic equation. So we've got -b plus minus the square root of b squared minus 4ac over 2a. And you've probably memorized it by now. In fact, I'm going to scoot it over here. So x is this, which in our case is -7 plus minus -7 squared minus 4 times 3 times 2 over 2 times 3. I get 7 plus minus, and then I get 49. Let's see here. 7 squared is 49 minus 4 times 3 times 2 minus 24 over 6. So 49 minus 24, nice, puts me at 7 plus minus the root of 25 over 6. Oh, turn my 6 into a triangle. So the root of 25 is, of course, 5. So I get 7 plus minus 5 over 6. So I get 7 minus 5, 2 over 6, and 7 plus 5, oops, and 12 over 6. 2 over 6 is 1/3, and 12 over 6 is 2. Right? So what we've got here is remembering that x, right? X is actually sine theta, right? And so what we can do is recall that x is actually sine theta. So we have sine theta is 1/3 and or actually it might get confusing. and 2. So let's see here. What were we trying to do? Solve the following equations by factoring. So sine theta is 1/3, and sine theta equals 2. I'll write it out properly. And sine theta equals 2. We can check on our unit circle here. I don't see any 1/3s or 2's on here. 2 would actually require more than a unit circle, and so for us, I'm ready to just call this solved. We could use the inverse, right? Use sine inverse to solve for theta. Okay. These are in radians. Need to be in radian mode on your calculator. So what we've got is we've got sine theta is 1/3, so theta must be the inverse sine of 1/3. So making sure that you're in radian mode, I get the inverse sine of 1/3 is, so theta is roughly 0.3398369095. And same idea, sine theta is equal to 2, so theta is equal to the inverse sine of 2, inverse sine of 2 in radians. Can't do it. Oh, that's because 2 is not in the domain of sine inverse. But we didn't really talk about that in this course, and so we'll leave that for, we will leave that for calculus. Okay. Although I know they'll pretend that you should have covered it, but I think we did briefly. The domain of the inverse sine is from -π/2 to π/2, but that's okay. I'm not too concerned. We can use trig identities to solve trig equations, right? And so here just goes through a couple of different options, right? So if we have to solve this equation, you're solving for theta, and we can use trig identities. And then here we're solving the trig equations by using identities, but I think we'll leave that because we definitely won't use it this term. All right. I guess just for completeness, I should copy it in. Oops. Although it's in your notes anyways. All right, so hi, I see All right, so we will leave these. Oh. As exercises to the reader. How about that? Means you don't have to do them. Okay. All right. How about that? Wow, really plowed through that. Any questions? Let's see here. Do you guys have any questions? So that's the, no. That's great. Awesome. Well, then that's it. That's all I've got. So that's the end of the material. So maybe I'll do the classic, the end. Thanks guys. Yeah, so there is no final, right? Just to do a quick recap, because I saw that Devinder joined us. So there's no final, and that was our last class. So thanks so much, guys. I'll see you guys next year on campus, I'm sure. All right. Any questions before I close it all down here? All good? Okay. Oh, Devinder has a question? Yes? No? Did you have a question, Devinder? No? Okay. Well, oh, yeah, everyone have a great isolation break. Totally. All right. Then I am going to shut it all down. All right. Bye, guys. See ya.